The last talk of the morning is Yasuyuki Kawahigashi, and he will tell us about characterization of commuting squares.
Okay, thank you very much. So I thank the organizers for the invitation. I'm very glad to be at Harvard again. So today I'd like to talk about certain commuting squares, which are important in subfactor theory of Jones. And so this is related to topological order in dimension 2 and tensor networks and subfactor theory. So as many of you know, physicists study fusion categories in condensed matter physics, as we already saw in some talks here. We are interested in two-dimensional topological order, gapped Hamiltonians, and related to certain four tensors. From an operator algebraic viewpoint, they are regarded as a biunitary connection, which I'll explain, giving a commuting squares. So we study these problems from a viewpoint of subfactor theory in this talk. So the outline of my talk is as follows. So I first explain commuting squares, which is a basic notion in subfactor theory, and it's a formulation in terms of biunitary connections. And then I'll talk about four tensors and the two-dimensional topological order. Then I'll explain projector matrix product operators. This is a certain matrix appearing in condensed matter physics. Then my main result will be about characterization of certain commuting squares. So commuting squares like this. So we have four algebras, finite-dimensional fifth algebras, A, B, C, D. So they are just finite direct sums of full matrix algebras. And we have a trace on D, the largest algebra. We say this is the commuting square. If we have trace, we have a conditional expectation from, say, D to B or C to A. And if we look at the conditional expectation from D to B, from the bottom right to the upper right, we restrict this conditional expectation from D to B to C, the left corner algebra. Then we should get the conditional expectation from C to A. This is a notion of commuting square. So this is certain commutativity of a diagram. Then in order to avoid some not so interesting examples, we require that the span of the product BC with B in B and C in C should be equal to D. So we have two intermediate algebras, B and C, and basically they should generate the entire D in some sense. So this is just for avoiding some rather trivial examples. Such a commuting square is called non-degenerate. And in this talk, commuting square means a finite-dimensional non-degenerate commuting square. So then we have the famous basic construction of Jones. So initially we have four algebras, A00, A01, A10, and A11. Then horizontally we can make larger algebras. So initially from A00 and A01, we can create a large algebra A02 by adding the so-called Jones projection. And basically, we can use the same Jones projection for the bottom inclusion, A10 containing A11. Then by adding the Jones projection, we get the large algebra A12. So A02 is now regarded as a subalgebra or A12. So this is a kind of simultaneous basic construction. Then we get a new square, A01 in A02 and A11 in A12. This new square is also a commuting square automatically. And we have a trace on A12. So we can repeat this horizontal basic construction to get the next square, A02 in A03 and A12 in A13. And we can repeat this procedure for infinitely many times. Then this gives the sequence of commuting squares, and then we can, so we always have a trace on these algebras. So using the trace, we can apply the so-called GNS completions. And so for the top line, we have an increasing sequence of finite dimensional fifth algebras, and the union is the union of A0n. And the second line, we have another union of A1n, and then we have this inclusion, and then we can take a certain closure of these two infinite dimensional algebras. Then we get a so-called hyperfinite type 2-1 factor. This is a famous von Neumann algebra, infinite dimensional operator algebras. Then the limit algebra A0 infinity and A1 infinity, they are hyperfinite 2-1 factor von Neumann algebras. And then in this way, we get a subfactor. So one factor contained in a larger factor. This is a subfactor in the Jones theory. Then, so this is a finite index subfactor in the sense of Jones. And in this setting, we get rigid C-star tensor category from a standard procedure using bimodules. Then we are also interested in the case of a fusion category, which means that we have only finitely many irreducible objects. And then in this situation, we say that the original subfactor has a finite depth. So this is a certain finiteness condition or something like a rationality in conformal field theory. But in subfactor theory, we use the terminology finite depth. Then this is a classical setting. And for this setting, we have another formulation of the initial commuting square ABCD. So for A contained in B, we have a Brattley diagram to describe this inclusion. So for A, we have finitely many full matrix algebra. So we have a dot for each simple summand. And also we have dot for each simple summand of B. Then if we have some inclusion from one summand to another summand, then we draw edges between them, possibly with multiplicity. In this way, we get a bipartite graph for the inclusion A contained in B. And also for A in C, we have another graph. For B in D and for C in D, we have, so we have 4 bipartite graphs. And then we take one edge each from these 4 Brattley diagrams. Then we get a square by using these 4 edges. Then we take a closed square in this procedure. Then we get an assignment of a complex number in this setting. So we choose 4 edges from 4 Brattley diagrams, and then from a combination of these 4 edges, we get a complex number. And this assignment is called a connection, biunitary connection. This name arises from an analogy to differential geometry. So this is a kind of discrete version of a connection in differential geometry. So this bipartite graph is a kind of discrete manifold. Then this biunitary, this name, biunitarity, means we have these numbers give entries of unitary matrices in 2 ways. So they are doubly unitary in some sense. And so this is our setting. So this biunitary connection is just an assignment of complex numbers to a square. So we have finitely many complex numbers with some unitarity assumption. This is our setting. Then so we have 4 edges in this setting. Then we write Xi1, Xi2, Xi3, Xi4 for these 4 edges. And then we draw this picture. This is a tensor notation. So we have 4 indices labeled by edges. And then we have an assignment of a complex number depending on these 4 choices. So we draw this picture. This is a 4 tensor because this value depends on 4 indices. And of course, it's well known that ordinary vector depends on 1 index. So this is regarded as one tensor. And for matrix, we have say AJK. So this number, a complex number, depends on the choices of two indices. So this is a two tensor. So we have three tensor, four tensor, and so on. This is a four tensor. So this pictorial combination of this kind of pictures is well known as a tensor network. So we have this kind of picture, a lot of tensors connected to each other. Then for connecting edges, we multiply these numbers and we have a summation of the indices for the common edge. So this kind of concatenation is well known in tensor network theory. So we get and in subfactor setting from commuting square, we get a finite family of commuting squares through basic construction. So in this case, we get a finite family of four tensors. Okay, so in the center of this picture, we have a circle. So we put some label for this circle. So in this way, we have a labeled circle. And so this is a finite family of four tensors. Then we have this notion of projector matrix product operator. So this is a picture. This is a kind of particular example of a tensor network picture. So, so we have circles, and all circles are labeled with A, the same symbol. So it means we use just one kind of four tensors. So we A, and so on. We have K circles. The number of four tensors is K. And then for the top edges, we label them as C1, C2, and so on up to CK. And for the bottom wires, we label them eta 1, eta 2, and eta up to eta K. Then for each this picture, four tensor represents a complex number. So we have K complex numbers. And concatenation means that we multiply these K numbers. And then for horizontal wires, they are closed. So we take a summation of all possible so we multiply these K numbers and we take summation of these products over horizontal wires, and also from the left, and also on the right most one, they are closed to a loop. So it means that it's just like a trace. So we have a product of these numbers, and we take a summation over this closed loop. And so if we fix Xi1, Xi2, and so on, and eta 1, eta 2, and so on, then this picture represents a number, a complex number given the summation of some products. So this is the number. Then this is a bracket notation. So for these choices of edges, Xi1, Xi2, and so on, we have ket vector labeled with Xi1, Xi2, and so on. And we have a bra vector, eta 1, eta 2, and so on. And so this is a ket bra. So this is a rank 1 operator with some coefficient before them. Then we take a summation of all Xi1, Xi2, and up to eta k. So this picture represents summation of rank 1 operators on matrices with some coefficients. So this is, and we have only finitely many choices, so this gives a matrix, just a finite dimensional matrix. And then depending on A, so all the other indices we have a summation. So this is a matrix depending on A. Then we also take a summation over A with some positive normalization constant dA and W. They are just positive numbers given by something. Then this is OAK. K is the length of this picture. So we have a summation over A with some positive normalization constant, then we get some matrix, just depending on K. And this turns out to be a projection. This matrix is a projection. And this matrix projection was considered by Brutink and other 6 physicists recently. And this is called a projector matrix product operator. This kind of picture is called a matrix product operator because classically they study matrix product states. Not operator, but this is a matrix product operator, and this is a projection. So this is called the projector matrix product operator. Then the range of this projection has some physical meaning on which basically they consider they are Hamiltonian acts. So this above projection based on four tensors is studied in condensed matter physics, and in this situation, we have finitely many quasi-particles called anyons. This already appeared in some talks here. So each anyon corresponds to a four tensor. So we have a family of four tensors, and this corresponds to a family of anyons. And then this operator is a finite-dimensional projection, and this range has a physical significance. So we started with a commuting square producing a subfactor in this setting of finite depth. Then we can construct another subfactor. So initially we applied repetition of the joint basic construction horizontally. But the situation is symmetric for vertical and horizontal directions. So we can also apply the vertical basic construction to get another subfactor, A infinity 0 and A infinity 1. Okay, initially I had A 0 infinity and A 1 infinity for horizontal basic construction. But for this one, I now have A infinity 0 and A infinity 1. So from the initial commuting square, we have a vertical construction, the horizontal construction, and they are somehow related to each other. And then it turns out that we can prove that the range of this matrix product operator is equal to the higher relative commutant of this subfactor from vertical construction. So in this way, horizontal subfactor and vertical subfactor are related through this kind of projection. This is we have something we'd like to study. Then that was my previous result on previous paper. Then my new main result is about this problem. So from this study, we are now ready to study this mathematical problem. We would like to know which four tensors produce subfactors of finite depth. Because this is a classical problem which has been studied since for say more than 30 years, I would say. So it's well known that different four tensors can produce the same subfactor. Then there are lots of rather trivial examples of this type. So it's natural to ask the following two questions. So which four tensors produce the finite depth subfactor, and when they produce the same subfactor from different four tensors. So the problem one is this one. We want to characterize commuting squares that produce subfactors of finite depth. So this is a purely operator algebraic problem, which could have been studied, say, 25 or 30 years ago. But from today's perspective in connection to condensed matter physics, we have a renewed interest in this kind of classical problem. And also the second problem is a further refinement of the first problem. That is, suppose we have a hyperfinite type 2-1 subfactor n in M. This is given initially. Then we want to characterize all commuting squares which produce this subfactor through this series of horizontal basic construction of Jones. So from deep classification of Popper, we know that we have a kind of canonical commuting square which produce the given subfactor in M. But there are lots of different commuting squares which could produce the same subfactor. So this map is not one-to-one at all. From a commuting square to a subfactor, this is not one-to-one at all. So we want to characterize when we have this initially given subfactor from this situation. Then, so we recently have a renewed interest in these old style problems in subfactor theory in connection to physics. So these two are purely mathematical problems, but from this viewpoint, in connection to condensed matter physics and other kind of physics, we are interested in this type of mathematical problems. And today, I'd like to explain my answers to these two problems. So, answer to the first problem. So, this kind of problem was initially studied by my former student Nobuya Sato many years ago, actually 1997. He gave a construction of the following form. Let n in M, P in Q are two subfactors giving Morita equivalent fusion categories in the following sense. So if we start with n in M, a subfactor of the finite index and finite depth, we produce a fusion category of nn bimodules. And also, we get the fusion category of mm bimodules. So from a single subfactor, we automatically get two fusion categories. And they are related to each other in some sense. And we say that they are Morita equivalent. This is a tensor category version of Morita equivalence. So we have, so from a single subfactor, we get two mutually Morita equivalent fusion categories. And for another subfactor, P in Q, we get another pair of Morita equivalent fusion categories. Then, suppose that say fusion category of n bimodule and pp bimodule, they are also Morita equivalent. So we have two subfactors and assume that they give Morita equivalent fusion categories. Then the following commuting square, this one arising from the endomorphism of intertwiners. So this Morita equivalence of the NN bimodule and PP bimodule, they are given by some bimodule, kind of generating bimodule for this Morita equivalence. So X, the NP bimodule. Then we look at this endomorphism space, intertwiner space of X and P. So this is a linear map from X to Hilbert space X to itself, commuting with the left N action and the right P action. This is the endomorphism space. Actually, this is a finite-dimensional linear space. And then from the right, we multiply the Q as the PQ bimodule. And from the left, we multiply M as the MN bimodule. They are relative tensor product operation. And we get a new endomorphism space. And then also from the, the lower right bottom corner, we also get another endomorphism space, and then we get natural inclusion. So we get 4 natural inclusions. So this gives a square of finite-dimensional C-star algebras, and then we have natural trace, and we have natural inclusions, and it turns out that they give a commuting square. This is easy to see, well known. And then so Sato considered this type of commuting square in his old paper. Then it turned out that his construction is kind of generic or universal. So his construction, actually some slight generalization, but essentially his construction covers all the commuting squares arising in our problem. So my main result says a commuting square produces a subfactor of finite Jones index and finite depth with repeated basic construction if and only if it is of this form. So this form given by Sato characterizes all the commuting square we are interested in. So this is our answer to the first problem I explained. Then the next problem, this is a refinement of the first problem, is also studied in this context. So we now consider problem 2. So it is easy to see that such a commuting square are far from being unique, as I said, because So we start with A00 in A01, A02, A03, but they skip intermediate step and just look at A00 in A0K. Then the basic construction is A02K and A3K, 4K, and so on. So this kind of skipping trivially produces the same subfactor, though the commuting squares are kind of different, only slightly, but they are different. Then this kind of trivial skipping gives the same subfactor. And another kind of trivial operation is that Sato reduction by non-degenerate projection. So we have initial commuting square, then we cut everything by a non-degenerate projection P for some projection in P. Then it's easy to see that this cutting doesn't change the resulting subfactor at all. So this is also a kind of trivial operation which preserves the resulting subfactor. And then, but except for these trivial operations, then we have essentially finitely many different constructions of a commuting square for a given subfactor. That is an answer I'd like to explain now. So this is our second main theorem. So a commuting square produces a given subfactor n in M. That's a hyperfinite, finite index finiteness. And if and only if it is of the above form in the previous slides, but now n in M is fixed. This is given, initially fixed. But now P in Q, this is an any arbitrary subfactor, but this should give a Morita equivalent fusion category to the n in to the given subfactor n in M. Then, we have now in this setting two subfactors, n in M and P in Q. One is given, one is arbitrary. But this arbitrary one must be related to the given one through Morita equivalence. Then then the previous slide gives characterization of all commuting square we are interested in. Then basically, so we, as I said, we see that we have only finitely many different commuting square for given n in M, up to this kind of trivial like skipping and reducing. So in this sense, we have only for given subfactor n in M, we have only finitely many choices up to this one. Okay, so I stop here. Thank you very much.
Question, microphone.
Hi, is it on? This is Dietmar Bisch. So in your second theorem, can you say anything about the graphs on which the commuting squares are built, of those finitely many?
So these graphs are how to say, multiplicity counting from Morita equivalence. So in principle, we can, we can determine all possibilities, but well, in practice, it's difficult. But if we know for a given subfactor, if we know all possible fusion categories which are Morita equivalent to the given one, like for example, in the Hagelap subfactor case, then we can determine all the possible graphs in this way.
So are those then all these module graphs?
Yeah, that's right.
Okay.
Mm-hmm.
Okay, I have a question.
Yeah.
So if you give this subfactor, you can produce a fusion category.
Mm-hmm.
Can you easily read out the 6G symbols from the W biunitary?
The biunitary connection is just a part of the data for 6J symbols. So if you
off them quickly, or you can.
No, which way from a 6J symbol to connection.
From the biunitary W to the all 6J symbol.
No, that's a difficult direction. So, in principle, it's possible, but in practice, it's very hard.
Yeah. I hope you can do it easy.
Yeah, that's hard. Yeah.
Hi, this is Sean Cui. Just have a basic question. When you said this full tensor produces a anion, could you explain what that means? Like,
Okay, so we have a fusion category And so each simple object corresponds to anyone. This is our
Yeah.
setting.
Yeah.
Then also each simple object also produces a commuting scalar in this setting. So they each produces biunitary connection. So in this way, from a finite family of anyons, we get a finite family of 4 tensors.
Oh, okay.
Through commuting for finite family of commuting squares.
Oh, okay. I see. Thanks.
Okay, so if you have no questions, so let's thank the speaker again.
Thank you.